Recording in progress.
Maybe I can just switch off the sound on your laptop. Yeah, it should be okay. Okay. Okay, so I think we can start. So today it's my great pleasure to introduce Professor Richard Ellis from the University College London. And I have the hard work to summarize in 2 minutes his career, which is not that easy. So Richard did his PhD at the Oxford University. And then he moved to Durham, where he became later a professor of astronomy, before moving to Cambridge. Well, for someone to get his PhD in Oxford, that's quite nice, where he became a Plumiam Professor of Astronomy before becoming the director of the Institute of Astronomy. Then he moved to Caltech in 1999, where he was the Steele Professor of Astronomy. And since September 2015, he's the Professor of Astrophysics at the University College London. So Richard received many prizes and distinctions across his career. I have some of them on my list here. For example, in 2008, he became a commander of the Order of the British Empire. That's quite funny. In 2011, he received the gold medal of the Royal Astronomical Society. In 2014, the Breakthrough Prize in Fundamental Physics. In 2022, the Royal Medal of the Royal Society. And last year, everybody, I think in this room, remember that he received the Gruber Prize in Cosmology. There is also another interesting number on Richard's CV is the total amount of money he gets to do research, $24.1 million to do research. He supervised 34 PhD students, 31 postdocs, including several French, if I'm correct. And you spend 753 nights at the telescope. This is incredible. And in 1995, you were a member of the committee that has approved the James Webb. And that's why today you're going to talk about progress and surprise in study of early galaxy with JWST. Richard.
Okay, thank you, Nicholas. Very nice to be back in Marseille. I was last here giving a colloquium in 2016, so 8 years. And a lot has happened in 8 years, largely in this area of early galaxies due to the James Webb Space Telescope. So this image is, of course, a gravitational lensing image. It's a cluster of galaxies. It was the first public image that was released at the White House by Joe Biden. And I think when Joe Biden described this image, he didn't really completely understand what was going on in this image, but that's okay because he had many problems to think about. So I got this slide from Nicholas, and it is amazing because I was an undergraduate here, 1968, and the most distant galaxy in 1968 was 3C295. It's a radio galaxy, and the redshift is 0.46. And it was measured with the Palomar telescope. And this redshift of 0.46 in 1960 was regarded as a highlight of the Palomar telescope because they were looking back in time to before the Earth was formed. And since then, as you can see, the most distant spectroscopically confirmed object has gone from 0.46 to 14.3. And the age of the universe at a redshift of 14.3 is only 250 to 300 million years. So the universe is only 2.5 or 3% of its present age. And so this has been a revolution, I think, during my career. And it's not over because James Webb has only been in operation for about 1.5 years or just a little bit more than that. So it really is an amazing time. So, yeah, it's not working.
Okay. That's why I was saying there.
Okay. So what are we talking about here when we talk about the early galaxies? So this is obviously a cartoon. So time is running from left to right. This is the Big Bang, 13.8 billion years ago. And as the universe expands, it cools. And eventually the temperature of the universe of the plasma goes down so that the electric force between the proton and the electron can couple and form the hydrogen atom. So the hydrogen atom forms when the universe is about 380,000 years old. And that corresponds to when we see the microwave background. So at that point, the electrons are captured by the proton. And so light now can travel in straight lines without being scattered by electrons. So we see the microwave background from that time. But there are no stars or galaxies. The universe enters a dark period, which we call the Dark Ages, just hydrogen clouds. But the universe has dark matter, and dark matter is, is not a baryonic material. So it's separated out of the expansion of the universe already. So the dark matter is already clustered under its own mass. And so the hydrogen clouds collapse onto the dark matter. And eventually, as they collapse, they heat up and we get nuclear ignition. We get starlight for the first time. And, in the business, this is called cosmic dawn, the moment when the universe is first bathed in starlight. And that is one of the goals of the James Webb Space Telescope, is to directly witness this. So these stars are, for a given mass, they're not like the stars in the Milky Way because they haven't got any heavy elements. So the atmospheres are free from the metals that cause absorption in the atmospheres of stars. So for a given mass, they're much hotter than the stars that we see today in the Milky Way. So they emit an enormous amount of ultraviolet light. And that ultraviolet light, those ultraviolet photons, ionize the gas and create these giant ionized bubbles, which become more numerous as more stars collapse. And of course, as these bubbles expand, they overlap. And this process of ionizing the hydrogen in the intergalactic medium, we call cosmic reionization. Now, this is a theoretical picture, but of course, this period of reionization, when the universe starts as a neutral gas and ends up as an ionized gas, has been explored initially with telescopes like the VLT and Keck and Hubble, but now James Webb takes over in much more detail. So for the first time, we have the capability now to observe this period. So the questions are very simple. I mean, this is the frontier. It's very simple questions. When did this cosmic reionization begin and end? Would we recognize a galaxy that's just emerging from darkness? Presumably, it wouldn't have any chemical elements other than hydrogen and helium and a little bit of lithium, which are made in the Big Bang. And then this reionization, this picture, where it's driven by galaxies, it's like, what about black holes? What about decaying particles? So there are other sources of reionization. And so, there are a byproduct of questions of where did the supermassive black holes in the centers of galaxies come from, and so forth. So here's the launch of James Webb Space Telescope. Nicholas was almost there. He left just so that he could get home for Christmas. He would have seen the launch if he'd have stayed, but his Christmas was more important, so he came back home, and he missed the launch by, what, 1 day?
Less than 24 hours.
Yeah, right. So your dedication wasn't good enough to witness the launch of James Webb, but that's okay. All right, so what do we know about reionization? Well, what is reionization? It's the generation of electrons. I told you at the beginning of the universe, it's very hot, so there's lots of electrons. Then the hydrogen atom forms, so the electrons are all captured. So reionization is the photons from galaxies, the UV photons that break the hydrogen up all over again. So the universe today is fully ionized in deep space. So there's a column of electrons in the universe from when reionization begins right up to the present day. And those electrons polarize the light from and scatter the light from the microwave background. And so the Planck satellite measured this polarization very carefully, and they reckon, the Planck team reckoned, that the universe was probably neutral, hydrogen and the hydrogen atom was still in place at a redshift of 11. And in a very rapid period, from when the universe was 500 million years old to 1 billion years old, down to a redshift of 6, there was enough radiation to completely ionize the intergalactic medium. And the peak, the peak period when reionization was sort of halfway through would be about a redshift of 8. So on that basis, this period is, when so we would imagine then, if the Planck people were correct, that the earliest galaxies would be around here, around a redshift of 12, maybe, something like that. And so people have tried to, before James Webb, people tried to estimate when reionization ended. And the measurement we make is what we call the neutral fraction, the fraction by volume of the universe that contains neutral hydrogen atoms. And if it's 100% or 1 for the fraction, then, it'd be around a redshift of 12 or so. And if it's 0, corresponding to when the universe is completely ionized, then of course it would be 0. So these are measurements, and I originally had some slides in on this, but in order to keep the talk simple, I removed them. But these are measurements made, for example, through looking with quasars. Quasars act as beacons that highlight the so-called Lyman alpha forest, and the measures of those Lyman alpha forests tell us, how neutral the intergalactic medium might be. And so you can see that the observational data doesn't go really beyond a redshift of 7 or so by various techniques here. The Lyman alpha signal in galaxies, the Lyman alpha absorption in quasars, and so forth. So with Brant Robertson here in 2015, we took the Hubble census of galaxies and we made some assumptions about the stars within those galaxies and the ionizing radiation they produce. And we assumed naively that all galaxies have the same ionizing capability. The big ones obviously produce more photons, but in terms of their star formation rates, the ionizing properties were a constant. And we produced this curve, which suggested that most of the activity, happened, this is blue curve, I'm sorry, this curve here, most of the activity happened quite early, between a redshift of 12 and 8 or so. And you can see it doesn't fit the data very well. If the data is very accurate, and of course one can always argue it's not, then it seems to finish more rapidly. And so Rohan Naidu at Harvard, suggested that this rapid end might be due to AGN activity. In other words, as AGN begin to develop, their spectra, of course, are non-thermal. So there's a power law synchrotron, power law slope. And so their UV capability is much higher. And also the fraction of those photons that get out is higher. And so that may finish it off more rapidly. So I talked about the census of galaxies from Hubble. And that was done in 2 very separate ways. One is the so-called ultra-deep fields, and the last ultra-deep field was a collaboration, this is still when I was in California, between Jim Dunlop and the group at Edinburgh, seeing familiar faces here perhaps, at the Royal Observatory in Edinburgh. And this was one deep image that was taken with the infrared camera on Hubble. And in this very small area, there are 3,000 galaxies. It's 3 arc minutes, so a tenth of the diameter of the full moon. And we found for the first time 7 galaxies whose photometric redshifts, so just the colors of the galaxies, were beyond a redshift of 8.5, with the most distant one here claimed to be 11.9. Now, I want you to remember that 11.9 galaxy. It was seen in only 1 filter with Hubble, and all the other filters had no signal. And we argued that this was the Lyman break, just at 1.5 microns or so. And of course, we were ridiculed. How can you measure the redshift of a galaxy with the detection in one filter? So we were very cautious in this paper in 2013 about this particular object, but I want you to remember it. The other technique, very familiar to many people here, is gravitational lensing. And of course, Hubble also undertook some very long exposures on 6 clusters, so-called frontier field clusters. And here's one of them. And, you know, I love these images because all of these numbers refer to multiple images, which mean that you can measure the lensing properties, the power and the magnification properties of this cluster. And that gives you, of course, an additional boost to what you would see from an image like this one. But there are, of course, negatives. You know, the magnifications might be uncertain. The field of view is reduced because, you know, the focusing properties of the cluster reduces the volume that you actually see behind it. So, so there's some cosmic variance, and that's why 6 of these clusters were taken. So as we get to the launch of James Webb, this is where we were. So these two programs, the ultra deep field and the gravitational lenses, calculated the census of galaxies out to a redshift of 10, you know, with maybe 1 or 2 objects of dubious nature beyond. And you can see there's some uncertainty as to whether the curve is going down steeply. We'll come back to this curve later, or whether it's extending. And so, you know, in terms of whether there are galaxies beyond a redshift of 12, remember that's where the Planck team said things might begin, you know, depends critically on, you know, the final data point. So it was tantalizing, and there was a lot of debate in the Hubble community about, you know, what to make of this uncertainty at a redshift of 8 or so. So here we are. And I was very privileged to be in Caltech in February 2020. It was the last trip before the pandemic closed the United States to, at least to Brits. I don't know about Europeans, but we weren't allowed in. We were obviously considered very dirty. And here's a human, and this is James Webb in the clean room at La Laguna. And, you know, we were given a tour, and, you know, it's almost a religious experience to see this thing. It's 6.5 meters, 18 gold-coated segments, folded up, as you can see. Here's the solar shield, you know, size of a tennis court. And for me, as Nicholas mentioned, I was the only European-based astronomer on the committee called JWST and Beyond in 1995-96, which recommended what we call the Next Generation Space Telescope. And in that report, and I ask you to go back and read that report, there were 2 pillars of science that we made for James Webb. One was early galaxies, and the other was exoplanets and their atmospheres. Now, early galaxies was already a big theme with Hubble, as I've shown. You know, it's already, the first deep field had already been taken. But exoplanets was nowhere on the map. So that report was very visionary in foreseeing, you know, that exoplanet science would become big business over the next 20 years or so. So from 1996 to 2021, you know, the launch at Christmas is, you know, is a huge period of time, actually. And it was nearly cancelled a couple of times, as probably many of you know. But it's been a fantastic adventure. Now, what is special about James Webb? And so I'm trying, what I'm going to do is review. I've worked on some of the data myself, of course, but I'm going to try and give you a few highlights of what's happening and where the surprises are in what we're learning about early galaxies with James Webb. And what are the technical advantages? Well, obviously it's a bigger telescope, so it's 6.5 meters compared to 2.5. So it's actually got something like 4 times better angular resolution than Hubble, and that's very important, actually. it's obviously, sometimes people say that it's a successor to Hubble. It isn't really, it's more like a successor to Spitzer because it is an infrared telescope. It only observes down to 0.7 microns or so. And it's got a very wide range of filters, including some medium band filters. You see, these medium band filters are much sharper than the broadband filters. And so when you look at the spectrum of a galaxy, then you can see an excess in one of these medium band filters that is indicative of emission lines. So, you know, it's very clever. Having this wider range of filters gives you crude spectroscopic evidence of particular nebular lines that you wouldn't get from a broadband filter. But even better than that, it is a spectroscopy mission. Now, Hubble has spectrographs, but of course its limited aperture and its limitations to largely optical and ultraviolet wavelengths is not very good for high redshift galaxies. But James Webb has very sensitive spectrographs. And so the rest frame optical, the familiar lines that we've worked on for decades, oxygen 3, the Balmer lines, oxygen 2, all those optical lines, which are very familiar to us for measuring chemical compositions and so forth, are visible out into the reionisation era to this particular galaxy at a redshift of nearly 8. So here's highlight number 1, and this may seem surprising because this is not so much the very high redshift universe, but it shows how the resolution and depth of the James Webb images has improved our understanding of when disks formed in the universe. So for many years, when I used to give talks on Hubble, I would show these 3 slides. But today we see a beautiful elliptical galaxy and we see a beautiful spiral galaxy. If we go to a redshift of 1, we still see these beautiful elliptical galaxies. We see nuclei in spiral galaxies. Maybe they're not quite as elegant as the galaxies we see today. But when we go to a redshift of 3, we see compact objects with multiple components. And so, you know, the message from Hubble was that disk formation really starts around a redshift of maybe 3 to 4, and gradually disks get thinner, and the kinematics, you know, in the simulations were matching what, for example, were being found with the VLT, with Symphony and other instruments. And so you can see that even the theorists were happy with this. So for example, if you go back to simulations in 2019 from the T&G group, you can see that the rotational motion, these are simulations, the rotational motion, V rot divided by the velocity dispersion, which measures the mix of energy in systematic rotation compared to turbulent motion, you know, is more or less absent by the time you get to a redshift of 4 or 5 or so. And likewise, the imaging morphology, you know, the disk galaxies would be down here, and you can see that they're, you know, by a redshift of 4 or so, you know, then it's not so dominant. So take a look at this. This is, I like this paper very much. It's from the Manchester group. These are images of the same galaxies taken from Hubble with the Candles field, which is one of the, you know, deepest images that was panoramic with Hubble, compared to James Webb. And so you can see objects like the ones I showed you that have, you know, lots of components and irregular forms. When you start looking at them in the infrared with greater depth, then you see that they really are spirals. And these are galaxies between a redshift of 1 and 4 or 5 or so. This one I think is particularly interesting. If you look at it in the rest frame, in the optical, which of course is the rest frame UV, then as you go to longer wavelength, of course it becomes much more regular. Now we knew about this. We were well aware that there's a danger when you look in with Hubble that you're seeing the ultraviolet, and that there would be what we called a morphological correction. And so people did very careful calculations to show this, but obviously we got it wrong. because the disk fraction, particularly in the most massive ones, is more or less constant over this redshift range. And that's been borne out by ALMA. So ALMA was the first way in which we really could probe the kinematics in the reionisation era. And this was first done by Renske Schmidt. And she found two redshift 7 galaxies. ALMA, of course, being an interferometer, has exquisite resolution. It's got sensitivity as well. Here is the kinematic map, with red obviously being recession and blue being the velocity of gas coming towards you. And here are two very nice galaxies, and these are the V over sigma. Generally, the condition in the expert world for rotationally dominated motion is V rot over 2 sigma greater than 0.4. And then Nicola and I and Japanese collaborators looked at this lens galaxy at redshift 9, and there's some evidence there that that object is rotating also. Now, this is very challenging, of course, but James Webb has come along and using the NIRSPEC spectrograph, galaxies beyond a redshift of 6. 3 of them here you can see show V over sigma greater than 1 as well. So this is from a paper earlier this year. So it's very clear that disk formation started much earlier than we thought. There's even some evidence that objects at redshift 10, we'll come back to this object. It's a very special object. It was one of the first heroic spectra that we got from James Webb at a redshift of 10.6. It's now been observed with the integral field unit, which is on NIRSPEC, and you can see, it's pretty marginal. This is just pixel by pixel velocities, and on this V over sigma plot, you see it's out here too. So jury is out. I mean, it could be a merger of 2 objects, of course. That's always a problem with such coarse data. So that's highlight number 1, that really everything we thought about disk formation, has been changed quite dramatically. Disks seem to establish much earlier, kinematically and morphologically, than they did as viewed from Hubble. So the second is to go back to this discrepancy. So I remember I told you we weren't sure whether the number of galaxies was falling sharply or whether it was extending. Now, there was a curve, I think, on the slide I showed you before, which was a theoretical prediction. So what is this theoretical prediction? This theoretical prediction, go back to the earlier slide, seemed to match the data really well from a redshift of 3 all the way out to a redshift of 8. And that theory is that the formation of stars is dependent only on the amount of gas that's in the galaxy. In other words, star formation has a constant efficiency with time. You give me a galaxy with a certain amount of gas by mass, and I can tell you the rate at which it forms stars. And it seemed to work remarkably well. But obviously, it doesn't anymore. Beyond a redshift of 8, the galaxies, this is the first result that came out of James Webb, so this is in collaboration that I did in collaboration with the Edinburgh group. You can see the number of galaxies continues more gradually out to a redshift of 13 or so, when the universe is about 300 million years old. And so there's something different about these objects than the objects below a redshift of 8. And I'll come back to the possibilities here. Here they are. We'll come back to these. Now, this first paper, all of these redshifts were estimated photometrically. And so, one of the obvious explanations might be that these objects are not at that great distance. They could be at a lower redshift. Well, the new developments are that Nicola and I are in a big program called the Primer program, and this is a 400 square arc minute. It's the largest cycle 1 program in terms of panoramic area. It has a very clever wide plus deep strategy that gives us a range in luminosity. And if you remember, Hubble found something like 7 galaxies beyond a redshift of 8.5. In this primer survey, we found 2,500 galaxies beyond a redshift of 5. And again, the declining number of galaxies as a function of redshift extends now to a redshift of 14. There's a tantalizing drop here. So this is one new development, just increasing the sky that James Webb has surveyed, only in imaging, no spectroscopy. And the other development is from the JWST team, the guaranteed time team, who in cycle 2 went extremely deep over a small area in 2 fields, 9 arc-minutes square. So contrast that with 400 square arc-minutes. So these 2 strategies are complementary. They spent an entire week of observing time, and they also find galaxies out to a redshift of 14. And although it's not on the archive yet, there's watch out for one of these objects has been spectroscopically confirmed at 14.3, so it's the current record holder. No galaxies beyond a redshift of 15, which might be consistent with this tentative drop here, but who knows? Now, what's going on? Why are these galaxies more luminous and abundant? It suggests that star formation is at that period, in this period of 100 to 200 million years, is more efficient than it is later. And there's various possibilities. One is that these galaxies are very young and they're still settling down. They could be, they could have a different initial mass function. They could have could be so compact that any dust that they form is expelled by radiation pressure. It could be that feedback hasn't yet established itself. It could be that they're bursting and we're seeing them at a special time. There could be, you know, there could be a bias here that these are objects seen in some peaking activity before they become more massive and then, you know, start forming stars more regularly. So all of these are possibilities. To address the question of whether the redshifts are correct, here's where we are on comparing the photometric redshift estimated by color with the spectroscopic redshift. And you can see it with, you know, it's really quite good. There's generally a bias that the photometric redshifts are a little bit higher. You can probably see the data points lie more on the left line here than the right line. And that's because the galaxies can have hydrogen around them, which can produce a damp Lyman alpha absorption, which shifts the Lyman break to a little bit longer wavelength. And that would naturally explain this offset. But by and large, the photometric redshifts are pretty good. So spectroscopy has begun, and you remember I asked you to remember this object which was only seen in one filter with Hubble. We were right. It's unbelievable. I never believed, you know, I was very worried that this, so we predicted this was 11.9 plus or minus 0.3, and here's the James Webb spectrum, and there's the Lyman break, very, very clearly you can see here at 11.6. So this retrospectively was the most distant object that was found by Hubble. Now, there was one catastrophic failure, and obviously, you know, that's a shame. The Edinburgh group were very excited about this galaxy that they claimed was at a redshift of 16.6. And this was one of the first sort of press releases from James Webb in 2022 by Callum Donnan et al. And he was a student, so you have to sympathize, you know, when a student is the first author of a paper. But it was really very bad luck. So Naidu claimed it might be at a lower redshift, that this break was a Balmer break at a redshift of 4.8. But our story is even more complicated than that. What is actually happening is that there are extraordinarily strong emission lines, optical emission lines, oxygen and Balmer lines, that make these data points appear to be a continuum. And these lines of oxygen and H alpha land in these two filters and create the appearance of alignment break. And so it was really bad luck. And so within this redshift range, there's real ambiguity between a redshift of 5 and a redshift of 16.6. But that's the only really, if I go back, it's not on this plot because the student in question, finished the plot at 14. He didn't want to show his failed redshift, but redshift 16.6 or so. But that's the only real howler, I would say, in the redshifts. So I just go with one hypothesis for this excess of objects, and it's from Andrea Ferrara at Pisa, who's very excited that these excess galaxies beyond a redshift 10 are because we're entering a dust-free era. And what he suggested is that if you take the star formation rate of the galaxy, and particularly the star formation rate per unit area of the galaxy, which is sometimes called the specific star formation rate, then you can calculate the radiation pressure that would blast the dust out of the galaxy. And so he predicted that the dust-free era would be at around a redshift of 10. And so many of these galaxies would be less absorbed by dust than the galaxies at earlier times. So the question to the observer then is, do we see a marked change in the dust content beyond a redshift of 10? Now, you might say, oh, well, let's go and work with ALMA, but really that would be very challenging with ALMA to see the dust. So the only alternative way is to measure the ultraviolet slope. The ultraviolet continuum, of course, is grossly affected by the presence of dust. And so that's being done. And the general way this is done is you measure the slope of the ultraviolet continuum, which is rising as you go to shorter wavelength. And this beta, this coefficient, measures whether there's any dust or so. And so what you see, there are two spectroscopic samples here, one from Robert Storsani, the other from the Geneva group. And you can see that they measure the ultraviolet slope in their spectra, which is, very reliable because if there are emission lines, you can measure the slope around those emission lines. And you can see there's a lot of scatter. The average is plotted here and here for different luminosities. And you can see that as you go to higher redshift, the galaxies do get more and more dust-free. There's no obvious break. It's not as if suddenly you get in a complete new territory beyond the redshift of 10 or so. Now, for the aficionados, what do we expect? For a very young stellar population that has no dust at all, beta must be generally greater than -3. So you can see these measurements look, very spurious. Because you can't physically explain such extreme slopes. If you concentrate on the average, you can see it tends to about -2.6. Now, when you get to a very young stellar population that's very hot, you also have continuum from the gas itself, the so-called nebula continuum and 2-photon continuum. And that's actually redder than the starlight. So -2.6 is the so-called stellar and nebula limit. And you can see that it's more or less. So it's clear that the galaxies are dust-free, but there's nothing dramatic that would explain the Ferrara hypothesis. So I better move on. Highlight 3 is black holes. So, the question here is really fundamental. We see quasars at a redshift of 7.5 or less with billion solar mass black holes. And how on earth do you form such a supermassive black hole in only 900 million years after the Big Bang? And it's very difficult to do it from stellar mass black hole remnants, from type 2 supernovae or top 3 supernovae. So in the business, there's now, although there's no observational evidence yet, there's the general idea that a black hole, a massive black hole, could collapse without ever going through stellar evolution. You get a gas cloud, and maybe it doesn't fragment into individual stars for some reason. It doesn't cool, perhaps, or it doesn't fragment, and it collapses directly into a 10,000 mass solar black hole. So to understand this, we need a census of black holes in the reionization era. So how could this be done? Well, James Webb is a spectrograph, so we can look for all of the AGN features like broad recombination lines. It's probably too difficult to use X-rays because we just don't have, even with Chandra, we don't have the sensitivity unless there's a strong lensing. And then variability might be a chance, but of course you need a long time because the time dilation, the light curve of variability is stretched by 1 plus redshift. So at a redshift of 8, that's 10 times nearly. So you'd have to do a long baseline in time. So I'll go through these results. It's at an early stage. So the first person really to look for this was Harry Kana, who was a postdoc at UCL when Nicola was there. And he looked at the public data in the first year. And he found from 185 spectra taken in the first year or so, he found 10 AGN between a redshift of 4 and 7 from their broad lines. And the first thing you see is that if you use the standard Jenny Green and Lewis Ho relation for measuring the mass of the black hole from the width of the line and the compact nature of the broadline region, then the mass of the black hole, which is shown on the y-axis here, compared to the stellar mass of the galaxy, it lies above the relation for local black holes. So in other words, that it would suggest that it's very fast, that the black holes have grown faster than the galaxies at this early time. The second result from his work is that there were many more of them than we expected. So 5% of the population of galaxies from his sample. Here's a very good example of a genuine, what I think is a sort of gold standard. Here's a galaxy at a redshift of 8.5 from Kokorev et al. In the, I think it's in the Uncover survey. And here are this is O3 and the doublet, and you can see it's relatively narrow. And if you fit the line profile of O3 and then apply it to H beta, you can see that the H beta is much broader. 3,400 kilometers per second is too great for outflows. So this is a pretty good evidence of a 10 to the 8 solar mass black hole when the universe is only something like 550, 600 million years old. Now, I asked Lewis Ho, who's a sort of world expert on this, what if the relationship that Jenny Green and Lewis Ho determined in 2005 just doesn't apply at high redshift? Could we be overestimating the mass of the black hole? Because in this particular case, the black hole mass is 30% of the mass of the galaxy. I mean, that seems unbelievable. Here it is. It's way off the local relationship. Well, he said, yes, it could be uncertain, but probably not by more than a factor of 3. Now, this is a log scale. So, it's going to be very difficult to argue that this isn't a very massive black hole. So the next development, and it's very recent now, is Jode Mate in Austria, in Vienna, did a H-alpha selected sample from slitless galaxies and found many of these broad H-alpha line galaxies were incredibly compact and very, very red and dusty. And he called them little red dots. That's exactly what they look like. And Jenny Green went and got spectra of 17 of them and confirmed that they were broadline AGN, something like a 60% success rate. Now, there's some controversy about how many of these little red dots are AGN, because if it were a dusty AGN, then you would also you would expect signal in the MIRI, in the mid-infrared, in the MIRI detector. And not all of them show that excess in the MIRI detector. So it's possible that some of them are, some of this red light is due to starlight. But they have a characteristic SED. They have a red continuum in the rest frame optical, and in the UV they have a rising continuum. And so this characteristic V shape is a puzzle. You know, we don't understand if this is starlight and this is AGN, dusty AGN, or what. There's one object at a redshift of, let's see, I think it's 7.8 or something, that is gravitationally dense. So we can actually resolve this object and say it's got to be smaller than 30 parsecs, and it doesn't even seem as if it has a host. So, you know, makes you even wonder whether we're just seeing a naked black hole with some dust around it. So these are very interesting objects. So we've done a big survey using this primer imaging catalog. This is just out on the archive about a month ago. It's just got a referee's report. And we've found 340 of these little red dots. And here's their photometric redshift distribution. And you can see they, although we would be sensitive to them at low redshift, they seem to disappear at a redshift of 4. They seem to be an early phase population. And obviously we're still unclear what the physical nature of these objects are. But one idea is that, you know, basically that they're primarily a high redshift population, because initially the obscuration is coming from the galaxy itself, not the torus around the black hole. And as the galaxy grows, then of course it becomes larger, and so you don't see that dust obscuration, and so the galaxy isn't as red, and that would explain perhaps why this is particularly a high redshift. Now there are some claims in the literature for AGN beyond a redshift of 10. I'm skeptical. There's this paper from the Yale group. This is a cluster, Abel 2744, very famous cluster. And there's a Chandra image here, which you can see. And there's a blip here of X-ray emission, which lands right on one of the galaxies that was seen by the GLASS team at a redshift of 10. Now, it could be a coincidence, you know, I mean, how many, you know, it's not a particularly significant, it's a 4 sigma blip, this flux. Is it is it just structure in this X-ray map, or is it actually X-ray emission that's magnified by something at a redshift of 10? Well, they got a spectrum of this object eventually, and there's no evidence of AGN activity in this object. So, you know, I think the jury's out on this object, in my opinion. And then this galaxy that I showed you before with the redshift 10.6 bunker got this beautiful spectrum, and you can see all of these beautiful emission lines in it. So Roberto Maialino thinks there's a 10 to the 6 solar mass black hole here, because there are some very high ionization lines of neon. There's a P Cygni profile here for carbon-4. You know, but you know, it still could be consistent with, this is only 800 kilometers per second, so it still could be stellar-driven outflows. Now, variability, it's really hard work. So we've been working with Matt Hayes in Stockholm. I told you about the ultra deep field in 2012. We revisited the ultra deep field 11 years later, and we found 71 variables, and 3 are at high redshift. 1 is confirmed as an AGN. And, you know, this is what a light curve looks like over, you know, over 20 years or so. So you visit the field in 2010, you visited in 2012, you visited in 23, and you know, this is really hard work but what's interesting is that just finding 3 variable objects in the small field of the ultra deep field actually provides quite a competitive constraint on different models of seeding black holes. So we could come back to this if there's time. And finally, chemical evolution. Well, JWST has opened up the prospects for tracing the chemical evolution. So some of the highest redshift galaxies, we now have all the ultraviolet lines that allow us to look at the metallicities, and the metallicities are now down at the 10% or less solar. And so here are 2 surveys, one that looks at the so-called mass metallicity relations, as this mass metallicity relation has been known for a long time. Here it is at redshift 0. So at redshift 3 and all the way out to redshift 6 to 10, you can see the metallicity is declining. And here again from Robert Spersani is the mean gas phase metallicity. Here's solar going from a redshift of 6 down to something like 5% solar. So the prospects for making these measurements. Now I skipped over a slide, but there are many arguments about how accurate these strong line methods for measuring the chemical composition are. Robert Spersani calibrated his strong lines with a very nice analysis by Sanders et al. Of the direct method, which uses this auroral line of oxygen, which is collisionally excited. But it may be that ALMA can play a role here too, because there's an ALMA line that's insensitive to the variables of temperature and electron density that make these evolutionary plots difficult to justify very accurately. So let's turn back to, did galaxies do the job of ionizing the universe? So what we need to know is the ionization rate, which is of course the number of galaxies, the nature of their stellar populations, which produces the ionizing photons, and how those photons get out of the galaxy. So gravitational lensing, thanks to Richard Bowens and others, still gives us the best luminosity function, because without lensing, we would only see some portion of the luminosity function. So all of the question of the faintest possible galaxies, which are crucial for measuring the integral of the light from galaxies, comes from the frontier fields. There's still not a real campaign with James Webb to use lensing. There are a few clusters that have been studied with James Webb, but there's not been a concerted search for faint galaxies at high redshift through lensing over many clusters. So we now know the integral of this to about 20% or better. The ionizing photon production rate is usually defined as the number of ionizing photons divided by the UV luminosity. And there's some evidence that that's increasing as we go back in time, but we're not sure. There could be biases there. And then the fraction of ionizing radiation that gets out into the intergalactic medium is very difficult to measure at high redshift, because there's still pockets of hydrogen in the intergalactic medium that obscure any leaking radiation. So the way we've been doing this is to correlate the positions of galaxies with the Lyman alpha forest in quasar spectra. So here's a quasar, you use the quasar to get the absorption, and then here are some quasar spectra. And here you can see that there are ionized patches here, and then you do a redshift survey of the galaxies in the same volume, and you correlate the positions of the galaxies with the spikes in the Lyman alpha forest transition. And that way you can estimate this escape fraction is 10% or so. So we're still, there's been this provocative paper on the web that there's too many galaxies to reionize the universe. I really don't think this is, I think it's premature to panic. They argue that if you take an escape fraction of 20% and you believe this increasing ionizing production rate out to redshifts of 9 or so, then reionization would end at around a redshift of 8, and you'd over-predict the polarization of the microwave background. But there's many biases in this analysis, I think, so I wouldn't worry about that. So let me end with cosmic dawn. You know, this was, it's in, if you go and read the Dressler report from 1996, it's in there. And how would we recognize a galaxy that's just emerging from darkness? It would be chemically pristine. Now, the problem is that, you know, if you do a simulation of how quickly POP3, you know, stars form and pollute the interstellar medium, it could be as short as 5 million years. So you would, you know, the chemical composition ramps up very, very quickly. And so you'd need you'd be extremely lucky to find a genuine metal-free galaxy. And then, you know, most galaxies at these early times then are likely to be a mixture of population 2 and population 3. I mean, the simulation suggests that the population 3 sort of disappears by a redshift of 10 or so. So there are 2 claims so far in the literature for POP3 from James Webb. One is from Myelino again, and he sees this helium line by itself in the vicinity of this galaxy at a redshift of 10.6. Here's that blip. And, you know, the spectrum isn't good enough to eliminate the presence of other species. That's the problem. You know, he thinks this is a very low mass galaxy with only helium and you know, hydrogen would be absorbed, of course. And then Eros Van Zelle has found this very metal poor galaxy. It's 0.03 solar in this straddling the critical line in this cluster, 0416, a redshift of 6.6 or so. So again, going back to the simulations, which I should have mentioned, were done with Harley Katz. We would require, for POP3, the burden of proof is very high. You need a strong helium-2 over H alpha, and you need a very low oxygen. And so here are those 2 objects. The green is Van Zelle's object. So it does have a very strong helium and a very weak Balmer line. Myelino's limit, he doesn't see H alpha, of course, so you know, it's too high a redshift for NIRSPEC. So there's no evidence, it's just a limit here. But the oxygen limits are still not credible enough. So in other words, the exposures are not long enough to prove that there's no oxygen in these objects. So it won't be easy, you know, and one possibility is to synchronize James Webb with the square kilometer array, because 21 centimeter surveys should see some coupling between the Lyman alpha and the first galaxies. And so that's very exciting because James Webb will overlap with SKA low, which is due to start taking data in 2028 or so. So I finished. So let me just say, you know, that, you know, right now it's very, very exciting. And I think it's extremely exciting because over my career, all of our facilities have done better than we predicted. So, you know, the Keck, if you go back to 1985, it's very helpful to sometimes go back and see what did these, you know, what did scientists think these facilities would do, you know. So if you go back and read the science case for the Keck telescope, spectroscopic redshift surveys near redshift 1 will be a major area of research for a 10-meter telescope. I mean, you know, that's amazing. And we've used Keck to go back to redshifts of 8 or so. The Hubble Space Telescope, well, you know, Williams took the Hubble Deep Field, and John Bacall, you know, thought it was really dangerous because, you know, it could be very embarrassing. He didn't think there would be any galaxies beyond the redshift of 2 in the Hubble Deep Field. And if you go to Spitzer, you know, the case for Spitzer was to perhaps see a redshift of 3. So, you know, Keck went to redshift 8, Hubble went to redshift 11.6, and Spitzer went to redshift of 9. So, unlike politicians, astronomers always do better than they predicted, okay? So thanks very much for listening. And if you enjoyed the adventure, you might consider my popular book on the quest for cosmic dawn, when galaxies were born. Thanks very much.
Okay, thanks, Richard. Do we have any question for Richard? Okay, yes.
Hi, thanks for the talk. Is there a working theory for this abrupt drop at redshift 50 that is maybe observed?
No, except that, my guess would be that cosmic dawn is not a discontinuity, that, things ramp up because, time is compressed at that redshift. So, I think it's tantalizing, but nobody's explained it yet because it's not that significant. It's a very marginal. Perhaps more interestingly is, if I can go back, that the deeper campaign by Robertson and co. One way back, I think. If you go to their paper, they calculate the probability of seeing galaxies beyond the redshift of 15. And so there's a nice discussion in that paper came out earlier this year of what that might mean. But there's been no theoretical analysis. I mean, the theorists predict anything you want because it all depends on the efficiency of star formation. And so the traditional theory, of course, was this. So, most of the models predicted that, it would be somewhere around here. And so now they're trying to come to terms with what's going on here. So they're still behind the observation.
Yeah, Nicola.
So thanks for the really nice and interesting talk. At the beginning, you mentioned that Planck with the CMB polarization can put constraints on the reionisation.
Yeah.
And that it should start somewhere on redshift of 12.
Yeah.
And then you showed that with JWST, you find some galaxies at redshift 14.
Yeah.
So why is it not captured by the CMB polarization?
Thank you. I'll decide on this. The Planck model is not a CDM model. It's actually, what's the word? Sort of empirical fit. And yeah, so this is in the Planck paper. With the redshift parameter, we obtained the redshift at the beginning of reionisation 10.4 plus or minus 2, disfavoring any major contribution from galaxies that form as and here's the curve. But that wasn't based on lambda CDM, it was based on the sort of parametric fit to their data. And so, people who looked at, did it in the context of lambda CDM, found that there is the possibility of a tail of partially ionized gas out to redshifts of, anything you want, 20. So the Planck people really, well, we had a big argument with this at the Gruber lecture, do you remember? Because Jean-Luc Pouget was there. And, he came up to me afterwards and said, we didn't really mean this, so forth. But there's a tail out here. So the PISA group calculated this folding in Planck, lambda CDM, some various other constraints as well. And, so there is, within lambda CDM, there's certainly the capability of matching the Planck data and having a tail beyond the redshift. I can explain in more detail later if you like.
Yes, Matthew.
Yeah. So if you're a betting man, what would be your explanation among the list of possible sources for the high redshift luminosity?
Yeah, I think the mode of star formation is different, and which is great news because it means we're probably close to the beginning. That's my optimistic view. Whether it's you know, that those massive stars at that time are allowed to go to higher mass, so the IMF is different because the gas is very, very metal poor. And there are models that predict what the IMF would look like if you had, you know, very, very low IMF, you know, well, very, very low metallicity because the cooling, you know, the gas balance is reduced, etc., etc. Feedback, you know, I think, you know, theorists love feedback because they can play with all the knobs, you know, there's so many various types of feedback. I'm not surprised, but I don't find that very elegant, but it may be that that's going on. I think we've ruled out dust. There's nothing that, you know, the galaxies are already very low dust content at redshifts 8, 9, and 10. I don't think there's suddenly a new era beyond the redshift of 10. Bursting, the bursting model is I was initially thought it was a good one, but then you need a large reservoir of objects that are in the off state. You know, you can't have everything bursting all the time. You know, you can't have everything bursting all the time, otherwise you're just a constant start. So there's got to be an off period. And so for the abundance to be so high, then there must be a larger number of objects beneath that are not, and that stretches the halo mass function at that time, I think, for it to work. So my bet would be, heaven forbid, the IMF. You know, that there are more massive stars at these early times, and there's some evidence for that now in lower redshift galaxies with Wolf-Rayet stars, which I didn't have time to tell.
Yeah, Samuel.
You showed that James Webb pushed back in his past experimental risks.
Mm-hmm.
And so I was wondering, what should we do with what about the merger rates and the evolution of the merger rate that we had measured before from JWST, I guess?
Yeah.
And what about the formation of elliptic curves? When does it fit in this new?
Yeah, there's a lot for the theorists to do to recover. You know, merging doesn't necessarily, it depends, you know, merging could just be increasing the velocity dispersion. It wouldn't necessarily, you know, if it's minor merging, it wouldn't necessarily destroy the disks. I didn't talk about ellipticals. There's some provocative claims in the literature that galaxies at redshift 4 and 5 that are passive and red, you know, that they formed all their stars at redshift 10. And some of them would have to be very, very massive and would defy, you know, the cold dark matter picture. But I think it's unlikely because you can't, you know, you can measure the age of stars, but that doesn't necessarily, and it could be old. The stars at redshift 5 could be old, but just because the ages of the stars are old, it doesn't mean the age of the entire system is old. It could be that it's made from mergers of two systems that both have old stars in them. So there's a lot of settling to happen. I think you've asked a good question. There's a lot of revision needed in the origin of the Hubble sequence, for instance. I mean, this idea that, you know, everything was lumpy at redshift 3 to 4 and gradually spirals formed and galaxies were quenched and ellipticals formed at redshift 2. It's clear everything happened earlier. And so there's a lot of uncertainty now in, you know, what the story is, I think.
Maybe one last question. Yes.
Yeah, so I was wondering whether you think that the Euclid fields could bring things relevant in terms of reliability.
Yeah, Euclid, you know, Euclid is about to have its first paper release, or about this month, isn't it? Yeah, so that's going to be very exciting.
Mostly for variability.
Variability, yeah, in principle. You need 10 years, you know. So, and what we found, and Nicola is on this variability program, what we found is it's very difficult to compare variability from different telescopes. You know, the filters are not quite the same, the PSF is not quite the same. So you really, you know, Hubble, we're trying to go, I mean, we've just submitted a proposal to look at the frontier fields again. So, you know, that was, when was the frontier field? 2016?
16, 15.
Yeah, 15, 16. So that's 8 years. It's best to go back and use the same instrument. So how long is Euclid expected to last?
6 years.
6 years. Yeah.
Okay, the last one for Eric.
Do you have some, so what is the prospect now for cake?
Yeah. So, you know, we spent 20 years using CAC.
Yeah, that's what you say. It
To,
goes up to 8 and
to
then
get to redshift 8, and it was painful. You know, we would spend 2 nights on one object with moss fire, and now you can do it in an hour and a half with James. You know, the young people just don't realize how lucky they are. So there's a big revision for an ELT. You know, now the good thing about ELT is it's going to have fantastic image quality. But, you know, it's not going to go beyond 2 microns. So, you know, you're not going to get the rest frame optical lines. And so I think James Webb, I mean, thank goodness James Webb is going to be there for 15 to 20 years. Originally, it could have been there just for 5 years or 7 years or so. But yeah, of course, this is one area of astrophysics. So it's in this area of astrophysics. You know, and, you know, we're not as enthusiastic about ground-based spectroscopy when it's so easy to do this with James Webb. It's a big change. Even Steidel himself, you know, he built Mossfire and he said it's, you know, it's over.
he said that.
Yeah, he said it's over. It was good while it lasted.
Okay, thanks, Richard.
Okay.
And Richard will be there today and tomorrow, and he's in my office.
Yeah, please come by if you have any questions.
What we can't remove that?
What's the matter?
I was looking out if I click there.
Yeah, I know. Problems with how it's.
How can I see that recording there?